Hello, everyone. Welcome to my presentation. Our research is about using the explainable machine learning for building energy modeling. And we have 4 team members, me, Zhang Wei, also Liu Fang, Wen Yonggang, and Bernard Ni from Singapore universities. First, what is energy modeling? And energy modeling is to design a computer model to approximate the energy systems. So traditionally, people used mathematics and simulation for energy modeling. For example, the Energy Plus. And recently, as we have the prevalence of the Internet of Things, and we have the access to more and more data, so people are starting to work on the data-driven energy modeling using the machine learning algorithms. So existing works for energy modeling mostly focus on the fidelity, say the modeling accuracy. And we know that normally for physical systems, they are complex. So naturally, the corresponding machine learning models should also be complex enough, so as to be capable enough to model the complex dynamics in a physical system. But when the machine learning model is complex enough, and intuitively, we can also imagine the model is hardly to be understood, and which means that it becomes a mystery box. So we barely know what happened inside. So then we cannot stop asking ourselves, fidelity is all we need or not? So basically, we can say that there are tons of the publications recently for data-driven energy modeling or related topics in academia. But in industry, it's also true that very few of them can really be deployed in industry. So the key idea is that we start to realize that fidelity alone is not sufficient to make our machine learning models practical. And for companies and industry, they should be able to understand the model dynamics, then they can trust the model and deploy the model accordingly. And besides, recently we have more and more laws and regulations to force us to make our system transparent and understandable and can be explained so as to be deployable in practice. So here we know that we need explainable and interpretable machine learning for energy modeling for practical usage. And here we would like to introduce our method and results. So first, we introduce our dataset. We use a publicly available dataset from Kaggle. This dataset is big. It has a size of 2.6 gigabytes and covers over 1,000 buildings. Then, based on this dataset, we train a machine learning model. And after we derive a model, we try to explain and interpret this model. So in our experiments, and we find that train-based models normally perform quite well for this dataset. But we also would like to mention that our methodology is not constrained, limited to any models, to certain models. And our method is model agnostic. So basically, we can deal with tree-based models and also neural network and also other models. And we consider both explainability and interpretability. And for explainability, it's basically the impact of the input to the output. And for example, it's the relationship between the input and output. And we can formulate the impact of an input feature as a function of the feature values. And for example, we show the relationship between the energy usage in Y direction and the building floor area in X direction in the right figure. And we can notice that, well, it's quite normal for us to know that when we have large floor areas, likely the energy usage is also high. But it's also interesting to observe that the increase pattern is not linear. Actually, it's non-linear. It's a concave function. And so not only we know the pattern that larger floor area consumes more energy, and we may also have the observation that perhaps large floor areas is also good for improve the energy efficiency in buildings. And also based on the finer granularity function and quantification, and they can also facilitate the further system level optimization. And besides explainability, and we also would like to discuss a little bit about interpretability. And we know that normally for a complex system, it's really hard for us to achieve both interpretability and fidelity. But now our question is that why that the system is too complex? And is that possible to make the system less complex? So it comes our idea for interpretability. And we would like to use a surrogate. And this surrogate can be small, can be interpretable, but we use this surrogate to approximate a local space instead of a global space. And our expectation is that when you are dealing with local space, the dynamics can be relatively simpler. So it's feasible and possible for us to derive small, accurate, and explainable surrogate and visualize the decision-making process. And here we introduce our case study for warehouse buildings, as you can see in the right figures. And first, we may observe that in the root node, we check the power meter type, energy meter type. And when we say the ID of tree, this one means the hot water. And we go to the right branch. And we know that immediately we know the expected energy usage can be quite a minimum. And it's also reasonable because normally when we are storing goods and we do not need much heating. And suppose we go to the left branch and we check the floor area and the meter type. And for example, for electricity with the meter ID of 0 and a small floor area, we can also observe the energy consumption can be quite a minimum. But when we are looking for the larger floor areas, then for both electricity and chilled water, then the expected energy usage can be quite high. And also we may notice that in the leaf nodes, they are pie chart. So basically those pie chart gave us the likelihood of the energy usage in fine granularity. For example, the light color can indicate the small energy usage, the probability of small energy usage, and dark color implies a high energy usage. So overall, we may say that tree-based visualization can be quite informative and intuitive, and especially in a local space. And finally, we would like to include some discussions, and potentially it can also be our future works. And first, we believe that explainability should be beyond machine learning models. And for example, in the beginning data stage, we also have to understand well. For example, can we trust our data? And is our data biased? Suppose the data quality is not there, then it might be meaningless for us to carry on to explain and interpret the machine learning models. And also it's true that for explainability and interpretability, it's quite practical. So often domain expertise is a must. But we also know that we are human. Then suppose, imagine we have too much information, then normally it's equivalent to say that we have 0 information. So we try to investigate if it's possible to reduce the workload for human and to figure out the proper level of human involvement. For example, we can allocate more resource and effort to the anomalies. And we can also trigger warnings and alarms based on threshold and certain pattern of the functions. And also, what if there is really some risks, and what shall we do? And who is responsible? And how can we deal with the customer relations? And those are all about risk management. And we also should pay attention to those aspects. And finally, in conclusion, we believe that explainable machine learning has true impact of industry applications. For example, in energy modeling, as we introduced today, and also comfort modeling, which actually is another of the work from our team published in IoT journal. Okay, so that's all my presentation. I welcome any questions. from you guys. Thank you.